All right, we're going to concentrate on SCADA systems, which are supervisory control and data acquisition systems. In particular, when looking at SCADA systems, they basically have the ability to perform a whole range of different operations, from data collection to switching through to absolute control from a remote area or a basically an unattached area, or even, as I say, remote right from whatever the central process is, say electrical generation and then electrical distribution. So you can have substations that are remotely controlled, that type of thing. So they can also be unattended, so you don't have to, say, mining operations, likewise with the electrical power stations as well, and distribution substations. So you could have, again, a mining, say, in Western Australia, but the laboratory and everything running computer systems is in Perth, for argument's sake, while the mine is up in the Kimberleys area, up in the northern area of that way. But the reality is that you're gathering data, making decisions, being able to manipulate switching circuits, controlling a whole range of different devices, but you don't have to be sitting in the location at all. So a formal definition coming from the IEEE is that SCADA is a collection of equipment that will provide an operator at a remote location with sufficient information to determine the status of a particular equipment or a process and cause actions to take place regarding that equipment or process without being physically present. So generally, the SCADA, as a process or as a terminology, refers to centralized systems which monitor and control entire sites or complexes of systems spread out over large areas. Anything between, as I say, on hundreds of kilometers away through to just on the other side of your plant, for argument's sake. Now, most control actions are performed automatically by remote terminal units, RTUs, or by programmable logic controllers, PLCs. Host control functions are usually restricted to basic overriding or supervisory level intervention. For example, a PLC may control the flow of cooling water through part of an industrial process, but the SCADA system may allow operators to change the set points for the flow and enable alarm conditions such as loss of flow and high temperature to be displayed and recorded. The feedback control loop passes through the RTU or PLC, while the SCADA system monitors the overall performance of the loop. For example, in the electric utility industry, SCADA usually refers to basic control and monitoring of field devices, including breakers, switches, capacitors, reclosers, and transformers. Now, microprocessor-based relays perform online monitoring and control operations, eliminating the need to have separate SCADA networks at multiple locations, which eliminates redundant sensors, wiring, transducers. Now, traditional switchboards, such as panels with mechanical switches, red and green lights, all that type of stuff, are now replaced by a graphical user interface, a GUI, accessible through a personal computer. Now, various sensors can collect performance and condition information on essential station equipment such as transformers, circuit breakers, and data is stored for future reference. This time-based data will be used to perform specialized functions and provide decision-making guidance to operators, maintenance planners, and engineering in general. Where do we see these kind of things? Well, as we said, it's mining, so industrial processes, manufacturing, production in general sense, as we talked about general, power generation and distribution, fabrication, refineries, conducted in continuous, batch, and repetitive or discrete modes, infrastructure processes, public or private providers, including water treatment and distribution, wastewater collection and treatment, oil and gas pipelines, electrical power transmission and distribution, communication systems. Facility processes, well, public or private facilities, including buildings, airports, and ships, for example, they monitor access and energy consumption of buildings and the type of things that they're able to turn on and off, reverse cycle conditions during winter, that type of thing. Some of the typical aspects of the subsystems of a SCADA system include the human-machine interface. So obviously, you're dealing with computers, sensors, but equally, a human's going to have to program those things, going to have to interpret those things, going to have to monitor those things. So the HMI, or the human-machine interface, is the apparatus which presents process data to a human operator, and through this, the human operator monitors and controls the process. A supervisory system, or a computer system, that gathers, acquires that data through transducers, and maybe that is online all the time, or maybe it's collected data and then analyzed later. So on the processes and sending the commands or the controls to the process to turn it on, turn it off, turn the temperature up, turn the temperature down. Remote terminal units, RTUs, connecting sensors in the process, converting sensor signals to digital data and sending that digital data to the supervisory system. PLCs, or programmable logic controllers, they're used as field devices because they're more economical, versatile, robust in some ways too, generally, flexible and configurable than special purpose RTUs. Communication infrastructure, connecting the supervisory system to the remote terminal units. Obviously you can use modems, wireless, fiber optic, satellite links, a whole range of different things. Standards, well, there's no single standard covers all SCADA systems and applications, but as you might imagine, many additional standards exist that discuss specific hardware and software components of SCADA systems, such as communication hardware, protocols, database compliance, and human-machine interfaces. Now, some standards related to SCADA systems are summarized in this coming table. Again, you don't need to remember these standards, they're just drawing your attention to the types of standards that are available. Now, SCADA architectures have over the time basically evolved. So the first generation became known as the monolithic, and they're the first generation of SCADA systems, which were identified by mainframe computers being used to undertake the computing process. Initially, SCADA systems were independent systems without any connectivity. You weren't connected to the other systems as networks didn't exist in those days. The remote terminal unit vendors developed wide area networks, or WANs, to facilitate communications between central point and RTUs. The communication protocols were often proprietary, and so vendors had great control and influence on the SCADA performance and development. So therefore, they're like specialized things. Hard to, anytime something went wrong or you ever wanted an update, you had to go back to the vendor. Also, first generation SCADA systems had high redundancies, as backup mainframe system was connected at the bus level and was used in the event of failure of the primary mainframe system. So as you might imagine, there's technology, computers, memory, communication systems, wireless, all that type of stuff have either evolved or become cheaper. Things have evolved as things have gone on. The second generation of SCADA was the distributed generation. That was the adoption of local area networks, or LANs, enable the distribution of computer data processing across multiple stations so that the stations are able to share and process data in real time. Individual stations were designated as being responsible for a specific task, and as a consequence, the size and cost of each station was less than the station used for that first generation of SCADA systems. The network protocols remained generally proprietary, so efficiency, development, and security remained within that vendor control. So again, you had to go back, pay for these kind of things to be updated or changed, or maybe modified to fit your system better. This meant, as I say, you're relying on the vendor for ensuring the security of your SCADA system as well. That's another key point. Not just the updates and things like that, but yeah, literally the security of your system. So security breaches by hackers were not publicized, as it was not in the best interest of owner operators and all the vendors in that, to acknowledge such breaches. Consequently, the safe status of SCADA system security was often overestimated and considered all. As time's gone on, the third generation is the networked setup. So network protocols become standardized, and as network SCADA systems become internet accessible, the potential for security breaches substantially increases. So protocol and security standardization has advantages for improving security monitoring and resolution of breaches, assuming timely maintenance and updates. And again, as time's gone on, that's become, the SCADA systems themselves have become, such that you don't have to rely on the vendor as much as you used to in the past. All right, well, we're just doing, let's have a look at a particular power system automation, just to give you some sort of idea. In order to assist in that explanation of SCADAs and the dynamics, let's have a look at this overview. So what is it? It's a power system automation. Power system consists of devices that generate, transmit, and distribute electricity or power. In the electric utility industry, SCADA usually refers to basic control and monitoring of field devices, including breakers, switches, capacitors, reclosers, and transformers. So here we go, we've got some data acquisition occurring, collecting the data in the form of measured analog current or voltages, values for open or closed status of contact points. Power system supervision carried out by operators and maintenance engineers through the acquired data that they're getting back from substations, generators, pumps, a whole range of things. And obviously that's graphically displayed. Power system control. Control refers to sending command messages to a device to operate. An INC, a collection of devices that monitor, control, and protect the instrumentation and control systems and the power system devices themselves. Who does that? Well, the power system vendors are following a trend to make devices smarter so they can create and communicate the required information. So if we talk about the smart grid, investigate that a bit as well, and you'll see that those things have certainly come of age. Applications in power systems, well, there's a whole range of things. So, it's not a checklist, but this is, again, just some of the key facets that we can go about using SCADA systems, automatic switching, and a whole range of, subheadings there, and a whole range of different applications, protection and control, transformer management, voltage regulation management, automatic system diagnostics, and maintenance safety. And the graphical user, the station MMI. So, again, it's just sort of giving you a bit of an overview. Now, the PLCs, or the programmable logic controllers, we'll have some laboratories focusing on that in particular, because industry has asked us to focus in on that. So we will be getting hands-on practice with some of the basic instructions relating to PLCs. A PLC is a programmable logic controller, or a programmable controller, digital device designed to control machines and processes by performing event-driven and time-driven sequential operations. So event, again, if you have to basically monitor the temperature and something happens when the manufacturing process, or might be in a cement works or something like that, you might have to increase the heat in the furnace and the kiln to create cement. Time driven, well, again, it could be a timer of some sort. So the fact of the matter is that electricity lights come on at a particular time and go off at a particular time. So again, it might be related to time-driven operations. Includes electrical and electromechanical processes such as the control of machinery in a factory, to amusement parks, to large and complex infrastructure systems. Now, PLCs are designed to operate in harsh industrial environments, and unlike a general-purpose computer, they're capable of handling multiple inputs and output arrangements. They operate in environments experiencing a wide range of temperatures and are immune to electrical noise and are resistant to impact and vibration, which can greatly occur in a whole range of industrial processes. A PLC does not require highly developed programming skills and operates as a real-time system, as it's able to respond to input conditions quickly. Initially developed for the automobile industry before the development of PLCs, the control, sequencing, and safety interlock logic for automobile manufacturing was accomplished by hundreds, indeed thousands of relays, cam timers, and drummer sequences and dedicated closed-loop controllers. The development of PLCs eliminated the time-consuming and costly yearly changeover process of the inflexible and hardwired relay panels for that specific vehicle model. So while the automotive industry remains one of the greatest users of PLCs, they are extensively used in a diverse range of industries. PLCs are programmed using application software on personal computers, with the computer being connected to the PL through Ethernet, your RS-232 or your RS-485 or your RS-4422 cabling connections. PLC programming software permits entry and editing of what's termed ladder-style logic. The software generally provides debugging and troubleshooting facilities, and this can be achieved by holding portions of the logic to show current status during operation or via simulation. Emulator, it's sometimes called an emulator or a simulator. The software will upload and download the PLC program for backup and restoration purposes. Some PLC models have the capability to transfer the program from a personal computer to the PLC via a programming board, which transfers the program to a removable chip, such as in the an EEPROM, basically. The advantage of PLCs are they're flexible, reliable, inexpensive, documentation, and efficiency. So flexibility, one PLC can handle multiple operations, and software changes are easier to implement than hardware modifications. One PLC obviously can run many machines if it can take many inputs. Reliability, solid-state devices are more reliable and easier to maintain than mechanical relays and timers. Inexpensive, PLCs benefit from the ability of computer systems to deliver increasingly complex functionality inexpensively. Documentation, PLCs can provide immediate snapshot of the current control circuit status. Efficiencies, the program alterations of wired relay type panels result in time-consuming and expensive rewiring. I mean, that's long gone in lots of ways. Whereas any circuit design, sequence alteration, or error correction involving PLCs is simple. Basically, you just retype the logic, reprogram it, Consequently, the turnaround times are extremely short in comparison and obviously much more cost effective. PLC functionalities, and we'll explore some of these when we look at the laboratory. And again, it's an introductory unit, so there'll be introductory things that we'll be doing. Timer functions, counter functions, sequencer functions, compared functions, it's just as I say, that's aromatic functions, control functions, data, move, all those type of things. We'll be exploring some of those things with the PLC, just again as a fundamental introductory well, exercise enterprise, to be honest. So you'll be asked to, say design a PLC ladder diagram like we see here. And the key thing, we have an emulator. If you look in your laboratory area, you'll have an emulator that you're able to use. So my suggestion would be that when you're testing these things out, get the emulator working. You'll be using that before you come to the laboratory, and also you'll be using the actual PLC, the physical PLC, when you come to the laboratory. But they are very, very handy to use to be able to put in your ladder, logic, program it, and see what your outputs are. So in this case, we want to design a PLC ladder program that will turn a solenoid on immediately after switch SW1 closes, and then turn solenoid B off 25 seconds later. So again, the best thing to explore is the emulator, and pretty much that's what you're going to do. All right. So if you put that into the emulator, you'll be able to, see what's happening. Again, it's like the mathematics. Playing with the emulator is a very, very good experience. So that's the best way to go about doing it. So if you check out the emulator, if you have problems with the emulator, check with our technician. Our technician looks after that. Just give them an email, etc., etc. But the key thing is go and program that into the emulator, and you'll see very, very quickly that it works quite well. And then, as I say, physically, when we do the laboratories, you'll be coming back to look at that. All right. So it's just a basic introduction to SCADA. So you have some terminology, you have some insight at least into SCADA systems. Again, the expectation is that you don't need to know SCADA systems inside and out, just as long as you're aware of them and the type of things that they're used for. The PLCs, as I say, you'll get some practical experience with those. The emulator is good. Do use it because it's a good test for just seeing the logic and testing it out, and particularly because you can see it light up and you can see what's happening and you can change things, and that's the key thing. Also, the physical PLC you'll get to use in laboratories. So again, all good practice.